Alrighty, in this video we are going to be talking about particle motion in terms of polar equations. So we have 8 derivatives that you might see, but honestly we can just manipulate some of these derivatives and you'll see what that means here. So like we should know these 3 from what we did here. So we know that for dy dx, that's going to be equal to dy d theta over dx d theta. Or it could equal dy dt over dx dt, depending on what you're given. For dy d theta, that's going to be y is equal to r sine of theta. So then to find dy d theta, that's going to be you using product rule and call it a day. Same thing here, the derivative of x with respect to theta, x is equal to r cosine of theta. Use product rule, call it a day. Now, for dy dt and dx dt, what you want to look at here is, honestly, look at this lovely thing right here, and knowing how that dy dx is equal to this right here, and just manipulate it so that you get dy dt or dx dt. So for dy dt, I could say something along the lines of, let's see, dy dx times dx dt. And everything that I could say is dy d theta times d theta dt. So using the chain rule of theta. For dx I could do the same thing using chain rule of theta. So I have dx theta times d theta dt. Or if I were to solve for dx dt here, I have dy dx divided by dy dt. No, wait. Dy dt divided by dy dx. All right, so for drdt, drd theta, and d theta dt here, I'm going to be using a chain again. So I have dr d theta times d theta dt, and that's going to be equal to dr dt. And then to find dr d theta and d theta dt, honestly, what you're going to do here is just divide to get your derivative here based off of this derivative right there. Now, whenever we are justifying or interpreting our answer, we want to make sure that we include the sign of r. So if r and dr d theta have different signs, then the particle is moving towards the origin. If they have the same signs, we are moving away from the origin. So this is honestly like PVA that we did back in Unit 2, back in AB with my signs. All right. Now, even though there are 8 derivatives, like I said earlier, you probably just need to figure out what derivative we're using and go from there. So for example, on number 7 here, we have r is equal to theta plus cosine of theta, and we have a particle traveling along the curve such that d theta dt is equal to 1/2. We want to find out what dx dt is at the instant when theta is 5 pi over 6 and interpret the meaning of our answer in the context of the problem. So here's the thing. We have x's, we have thetas, and we have t's. So I'm trying to connect all of those 3 variables with dx dt. So I'm going to have dx dt being equal to dx d theta, so the derivative of x with respect to theta, times d theta dt right here. Now we know that d theta dt is always going to be 1/2 right here, so I am going to rewrite this so that we have dx dt is equal to dx d theta times 1/2. And then to find out what dx d theta is, what we're going to do here is look at this lovely thing right here. That's r. And we can connect x and theta using r is equal to x is equal to r cosine of theta. So then I have x being equal to theta plus cosine of theta times cosine of theta. Take the derivative of x with respect to theta. So probably use product rule here, but I'm not going to do that because I can use our handy dandy calculator and figure out what that is at 5 pi over 6. Now, notation wise, you want to make sure that you have theta is equal to 5 pi over 6 here, and you want to write it right here. All right, so I'm going to go ahead and put this into my calculator. I prefer to write it in y1, just in case I have to revisit my equation. So I have x plus cosine of x times cosine of x there. Okay. And then what we're going to do here is go to math 8. Well, let's do second quit first. Math 8. Okay. What's going on, guys? Anyways, math 8, alpha trace y1, and we want this to be at 5 pi over 6. Which gives us negative 1.308. So I have negative 1.308 times that by a half, and we get negative 0.654 for dxdt when theta is equal to 5 pi over 6. So this is saying that the exposition of the particle is decreasing at a rate of 0.654 units per time whenever theta is 5 pi over 6. So essentially, my exposition is decreasing, aka it's going towards the pole. All right, so for number 8, we have r is equal to f of theta. We know that it is differentiable. We know the values at pi over 2 for my function and my derivative. And we want to find the slope of the tangent line to the graph of r is equal to f of theta when theta is equal to pi over 2. Now, I'm going to be honest, once again, I cannot remember the derivative to save my life, and every time I have to do this, I have to use product rule. That's just me, though. If you could figure it out and you can memorize this formula, then great. So I have first times the derivative of the second plus second times the derivative of the first. Okay, and then we have r cosine of theta. So we have first times the derivative of the second plus second times the derivative of the first. Okay, and then we're just going to plug in pi over 2. We know that pi over 2 here's 10, then cosine pi over 2 plus 4, then sine pi over 2. Theoretically, if you want to leave it unsimplified like this, you can. However, hopefully we know what cosine pi over 2 is and sine pi over 2. If we don't, then yikes. The cosine pi over 2's will cancel out. So now we're left with 4 over negative 10, which is negative 2/5. So this tells me that the slope of the tangent line when theta is equal to pi over 2 is negative 2/5. All right, for number 9, we have r is equal to 2 plus 2 cosine of theta, and we have a particle. that moves along the curve such that dr dt is equal to dr d theta. We want to find the value of dr dt at theta is equal to pi over 3. Interpret your answer in terms of the motion of the particle. One lovely thing about this is that dr dt is the same thing as dr d theta. So honestly, I can find out what dr d theta is because I have r with respect to theta right here. So dr d theta being equal to dr dt helps us find out that dr d theta be -2 sine theta. And then I'm going to plug in a pi over 3. So I'm going to plug in theta is equal to pi over 3. -2 sine pi over 3. If I were to think about pi over 3 here and sine, that's going to be root 3 over 2. So I get -√3. All right, so what does this mean here in terms of the context of the problem right here? So if I have a -√3, this means that my radius is going to be getting closer to my origin right here. So we can say that the particle is moving closer to the origin at a rate of √3, since we know that dr d theta, or in this case dr dt, is less than 0 whenever we have theta being pi over 3. Okay, so for this one here, we know that dxct is equal to dxc theta, and we want to find the value of dxct when theta is pi over 3. So good news for us. We have theta right here. That's great. So now we need to connect theta in terms of x. So that means that x is equal to r cosine of theta. We got to figure out what the derivative is at pi over 3. So we're going to be using our handy dandy calculator and say, say 2 plus 2 cosine of theta, or x in this case, and then cosine of x. Second quit, math 8, y1, and our theta value here is pi over 3, which gives us -3.464. So what does this mean? Well, this tells me that the x-coordinate of the particle is moving to the left at a rate of 3.464 units per time. Okay, number 10. We want to find and interpret the value of dxc theta at theta is equal to 4 pi over 3, given that r is this lovely thing right here. So once again, we have x is equal to r cosine of theta, and that's going to be 2 sine theta cosine of theta, and we want to figure out what dxc theta is at pi, and no, not pi, at theta is equal to 4 pi over 3. Now, hopefully you guys remembered your pre-calc skills and how this right here, 2 sine theta cosine theta, is an identity, and that this is equivalent to sine of 2 theta. If you didn't remember that, then honestly you could use product rule, but it's going to be a lot. But now, given that we know that x is equal to sine of 2 theta, I could say dxc theta is equal to 2 cosine 2 theta, see what we get, and call it a day. In this case, we have 4 pi over 3. So dxc theta, when theta is equal to 4 pi over 3, is equal to 2 cosine 8 pi over 3. let's see, 8 pi over 3. That's going to be 2 pi over 3. And if I think about 2 pi over 3, I am going to get a negative a half. So that's going to give me a negative 1. All right, so what does this mean? Well, this means that the x-coordinates of the particle is moving to the left at a rate of 1, because we know that dxt theta, not dxt theta, dxt is less than 0 when theta is equal to 4 pi over 3. All right, so we have B here. A particle is moving such that d theta dt is equal to 5 for all t, where t is measured in seconds. Find and interpret the value of dr dt whenever theta is equal to pi over 6. So let's see. We want to figure out what dr dt is. Right now, I have d theta dt, and then I have r in terms of theta right here. So let's see. I'm going to have dr dt. And honestly here, we could probably guess what this is right here. That's going to be my thetas right here. So I have dr d theta dt. We know that d theta dt is always 5. So now I have dr d theta times 5. And we want to see what's happening whenever we have theta being pi over 6. So now we could substitute in dr d theta. We know that was 2 cosine of theta. So 2 cosine pi over 6 times 5. So that's 10 cosine pi over 6. And pi over 6 is root 3 over 2. Which gives us 5 root 3. So we want to interpret the value of dr dt here if we have 5 root 3. Because my radius is getting bigger here and it's increasing, we know that we are moving away from the pole / origin. So we know that whenever dr dt, the rate of that is going to be 5 root 3 units per second, since dr dt is greater than 0 at theta is equal to pi over 6. All right, you should be able to do number 11, hopefully, and then we'll do more practice in class.